Gross-Siebert program. Please go ahead.
Okay, well, thank you. Let me just quickly review where we were at the end of the last lecture, where I was going to start on with sort of the rigorous development of the subject. So, as I said, first of all, we have the notion of a log-Laplace pair, and this will be, should be connected. So log-Laplace pair is going to be our generalizations of a good notion to work with to replace the notion of maximum impotent degeneration. So this should be viewed as a more general setup. So we have the pair XD. X is a non-singular projective variety. D is a simple normal crossing this divisor with Kx plus D equals 0. So it's what we call anti-canonical divisors, linear to minus Kx. So the typical picture, for example, for a surface would have D to be a cycle of P1s, like that. And I gave some examples. We have the toric variety with the toric boundary. We had P2 as smooth cubic, and we had the blow up of P1 cross P1 at a single point in the toric boundary. I introduced the notion of being maximally degenerate if there's a zero-dimensional stratum, i.e. some intersection of these boundary divisors is zero-dimensional. So, for example, the first and the third examples are maximally degenerate, but the second example with smooth cubic is not. Okay, and then I started to introduce some notation. So I had the group of divisors, div d of x is the group of divisors supported on D, so linear combinations of the di's. We have the dual lattice, so the linear combinations of di star, a vector space given by generated by the di stars. This. And then I built the so-called dual complex of xd as a cone complex inside this vector space. The cones are determined by subsets I of 1 through n. Remember that we have n boundary divisors. We look at subsets of 1 through n such that the intersection of all those di indexed by the set I is non-empty. And then you take the cone generated by the corresponding di stars. And B is the union of all these cones. So you can think of this as a topological space that comes with a polyhedral cone decomposition. And the examples I did last time, if you do take, for example, a toric variety, what you get back is something that looks like the fan defining the toric variety, but only as a piecewise linear object. So this sits inside R3. These are the 3 boundary divisors. The first boundary, the positive orthant in R3. Similarly for P1 across P1, you get something like this, but it's again sitting inside R4. And you can't tell the difference between P1 cross P1 and the blow up of P1 cross P1. Now, the crucial thing, and this is the first topic I'll discuss now, is that if D is maximally degenerate, we can give B the structure of affine manifold with singularities. So that's what I'm going to do now. A bit of notation. So given, so here again, fix XD maximally degenerate. Well, I'll call it the and dual complex, which I'll write as BP. B is the topological space, P is the collection of cones. So for a cone, sorry, technical problems. Okay, for a cone, rho in P, let's say rho is some sum. There's a sum I and some index set I, R greater equal to 0 di star. we can write, I'll write as X row. This is just the corresponding stratum, this intersection of all I and I of DI. So that's guaranteed to be non-empty by our fact that rho is in P. Now, if dim X is equal to, let's use D for the dimension, and rho, dim rho is D minus 1, then X rho is naturally one dimension. An intersection of D minus 1 divisors meeting transversely, and hence gives us something one-dimensional. And in fact, one can show, this is a somewhat non-trivial statement, one can show that X rho is in fact isomorphic to P1, and X rho contains two zero-dimensional strata, i.e., there exist cones, let's say sigma 1, sigma 2. Actually, let me use sigma and sigma prime for cone sigma, sigma prime in P with dimension of sigma, sigma prime equal to D, and X sigma and X sigma prime, both subsets of X rho. So particular rho is contained inside sigma, sigma and sigma prime. Okay, so this is a somewhat non-trivial statement in arbitrary dimension. I think it follows from results of Kohler and others. But let me just sort of go back to this earlier picture we had where in 2 dimensions, a one-dimensional stratum in this picture is just something like this. And of course, as you can see, it does contain 2 zero-dimensional strata. This is actually necessary to show that B is something that's fairly close to a manifold. It's not exactly a manifold, but it's close to. Okay, so one can show that. Okay. So now I'm going to define a affine chart in a neighborhood of rho. So let's let star of rho contained inside B be defined. Star of rho is equal to interior of the intersection of the union of these 2 maximal dimensional cells. So the picture, let's say we're in 3 dimensions, is we have 2 maximal dimensional cells, sigma and sigma prime, meeting along a cone rho. And the star of rho, of course, is just the interior of this union of 2 cells. And what I want to do is define an affine coordinate chart or what is psi rho from star of rho into RD. Okay, so there's a precise formula for this chart. So to do this, let's choose a basis, E1 through EN, so ED, for, let's say, ZD, sitting inside RD. We need to keep track of an integral structure on RD so that we can make sense of this as an integral affine manifold. Then also write so the cone sigma is some summation r greater equal to 0 di1 star plus dot 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 plus r greater equal to 0 di d star. We have d cones. And let's take the first of d minus one of these to be generators for rho. So if r greater equal to 0, di1 star plus dot 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 plus r greater equal to 0, d minus 1 star. So that makes sense because these are all standard cones spanned by basis vectors of give d dual, and rho is a codimensional one face of sigma, so I can take a generating set for rho and extend it to generating set for sigma. And similarly, I can also generate sigma prime again using the generators for rho and then adding one more generator, which I'll write as d I sub d prime. Okay, so here, I just tried to write this in this picture. This will be d I sub d star will be a generator here, and d I sub d prime star will be a generator here. Okay, so I'm going to define psi rho as a map, a piecewise linear map, actually on just sigma union sigma prime. A priori, psi rho is just supposed to be defined on star of rho, which is the interior, sigma union sigma prime, but it's not a big deal. I can restrict the map. So let's define psi rho from sigma union sigma prime to r d as follows, as well as a piecewise linear map. So on sigma, we define psi rho. Well, I just need to tell you what psi rho does on generators. So d psi rho applied to dij star will just be the j space basis vector ej. So in other words, I embed the standard cone, I embed the cone sigma in RD as the standard cone, just the positive orthant in RD. Now on sigma prime, since I want a piecewise linear map that should be continuous, we define psi rho of dij star. Again, those will be generators of, this is for j less than equal to d minus 1. I take this to ej. That has to be the case to be linear. We've already defined the map psi rho on rho, because rho is a face of sigma. And then I define psi rho of d prime star to be equal to minus ed, minus the last basis vector, minus, and now we have a bit of a formula here, summation I equal 1 to d minus 1 of d I, sorry, d, I shouldn't use I here, sorry. So use j equal 1 to d minus 1. So I will have dj dot with x rho times the basis vector ej. Okay, so here x rho is a curve. Let's look at what this means. dj is a divisor. X rho is a curve. And the intersection of something which is dimension 1, namely x rho, with something that's codimension 1, namely dj, makes sense as a number. Those things will have some intersection on it. Put another way, this is equivalently, if you're unfamiliar with these intersection numbers, equivalently, dj dot x rho is the first Chern class, or is the degree of the line bundle OX of DJ restricted to the curve X row. Okay, so hopefully that makes sense. We'll do an example in a few minutes. Try to unwind this. Okay, so this is the chart, and it makes sense as a piecewise linear map on sigma union sigma prime, and we decree that that's one of our affine coordinate charts. Now, for different row, note for a different row, for distinct row prime, either star of row intersects star of row prime is empty, in which case there's nothing to check. We don't need to check if the transition map is linear. But what are the transition maps? Psi row composes psi row prime inverse is linear. Or row and row prime are both faces of some maximal cell sigma. Of some sigma and P with dim sigma equal to D. In this case, star of row intersect star of row prime is just contained in sigma, and the transition map psi row composes psi row inverse. Psi row prime inverse is just a linear map identifying sigma with two different cones. It's actually a linear manifold. The transition maps are actually linear. i.e., transition maps are linear. Okay, so far I've defined charts on these star of rows. That still means I'm missing quite a lot, because it means I'm missing kind of meshing two cones. So now define delta contained in B by delta is equal to the union of sigma and P. Dimension sigma is equal to D minus 2, so the codimension two cones. We have now defined an affine structure on B0, which is B minus delta. And this turns B into a integral affine manifold with singularities. Okay, so I'm going to do a couple of examples. But first of all, let me just remind you that last time I talked about the SYZ conjecture and explained how affine manifolds with singularities played a crucial role. I showed you an example of such an affine manifold with singularities coming from the quintic threefold. This one has rather a bit of a different flavor, but it still is playing the same role. So the idea is that somehow from the geometry of the pair XD, we get fairly cheaply an affine manifold with singularities. And notice it doesn't use that much more information than we had in B itself. All we do is we encode these intersection numbers. Now, let me do a two-dimensional example, and maybe this formula will then make a little bit more sense. So the first example I want to do, maybe the only example I'm going to do, is X is the del Pezzo surface of degree 5. So this is obtained by taking P2 and blowing up 4 points. Blowing up P2 and 4 points. Chosen generally, just to be safe. And then well, okay, so I need to tell you what D is. And so it's well known that such a surface contains 10 lines. Once it's embedded in P5, contains 10 lines, or 10 what are called -1 curves. So X contains 10 -1 curves, i.e. curves C with self-intersection, C squared equals -1, and C isomorphic to P1. So these will be embedded as lines if we use the anti-canonical embedding of X in P5. So I can write, so it turns out we can find 5 of these lines, or these -1 curves. Which form a cycle of 5 P1s. So in other words, it looks like something like this. And that is 6. So let's try that again. And so each of these curves has self-intersection -1, a normal bundle with Chern class -1, with degree -1. And I'll label these D1, D2, D3, D4, D5. And in fact, I'll use D1 through D5, and D1 through D, the sum of these is equal to -kx. So it's a fun little exercise to write down. If you start with P2, and I'll just sort of flag this as an exercise. If you're unfamiliar with this kind of geometry, describe the classes of these lines, or describe these lines by the description of P2 of X as being P2 blown up at 4 points. Okay. Good. So now let's take let's draw the BP. So a priori, I just have 5 cones. Again, I want to think about this as an abstract piecewise linear object. For the moment, these cones are generated by D1 star, D2 star, D3 star, D4 star, and D5 star. And I want to think about how these affine charts behave. So let's look at the affine chart, first of all, corresponding to star of this. If I call this row 2, what happens? What's psi row 2 from star of row 2, R2? Well, according to the formula, D1 star was going to get mapped to E1. We have a basis E1 and E2, basis for R2. And we define D1 star to map to E1, D2 star maps to E2, and now D3 star is supposed to map to minus E1 minus, and the formula I had, if you look back at what I've written, sorry, I just realized, did I write this correctly? Oh, no, that's fine. I should have written minus E2, not minus E1. There should be 2 there, according to the formula we had earlier. And then I'm supposed to have what is really D2 dot X row times E1. Now, D2 and X row in this case, or X row 2, are actually the same thing, right? D2 is the divisor corresponding to this ray. X row 2, because row 2 is one-dimensional, X row 2 is in fact just the divisor. They're both the divisor D2. That's equal to minus E2 minus D2 squared E1, which is then gives us minus E2 plus E1. Something is wrong with this formula. Sorry. No, that's right. That's fine. Okay, so if I were to draw this, no, I know what's wrong with this formula. Sorry, I should look at my notes on this when I do this kind of thing. I have messed this up a bit. So I think I interchanged these two things because I was using this ray. So the first generator, if you recall, I took, sorry, let me go back here. This is the disadvantage of not having a blackboard. I took rho to be generated by DI1 star. So DI1 would be D2 star. DI2 star would be D3. I actually want to think of this as, right about this. I want to take D2 star maps to E1. D3 star maps to E2, so I'm going to take, D1 star maps to E2. So this is going to be sigma, and this is going to be sigma prime. So finally, D3 star maps to minus E2 plus E1. Sorry about that, it's slightly messy. So in other words, what I'm starting with is, here's the image of D1 star, of D2 star. Here's the image of D1 star. And then the next one, D3 star, that's sitting down here. Okay, so this is 0, 1, this is 1, 0, and this is 1 minus 1. That's just this expression over here. Okay, so that's the chart. So it's identifying the star of D2 stars, namely this open set here, with this. Now, if you know any torque geometry, or if you know enough torque geometry to interpret this picture, the crucial point here is that this looks like a torque variety. So this fan defines a torque surface with boundary divisors. So I'll write as D1 bar, D2 bar, D3 bar, corresponding to these three rays. With D2 bar actually compact isomorphic P1, and D2 bar squared is equal to minus 1. This gives you a picture that looks something like this. Inside a surface, you should bear in mind that it's a non-compact surface because it's not a complete fan. But the D2 bar, in fact, is a compact curve with self-intersection -1. So in other words, what we're doing over here is we're just writing down a fan that looks like it has a -1 curve in it. And that's really kind of what that coordinate chart is trying to do in all dimensions. It gives you a little toric variety, a non-compact toric variety, which contains the P1, which has the right intersection numbers with all the divisors visible inside that toric variety. It gives you the same intersection numbers that occur in the formula here. Okay. So this is the first chart. You can actually keep on going. So rather than writing down distinct charts for every one, what we could do is we could just continue. We could now do a change of coordinates or use a different basis for R2 so that the next chart, the chart associated with this ray, or I should point to the ray row 3, the chart associated with the start of row 3 agrees with this chart here. So let me try to put this together. So again, what we start with is D1 star, that's 0, 1. D2 star, that's 1, 0. D3 star, that's 1 minus 1. Now, I want to then continue this. I want to know where to put D4 star. Turns out the correct thing to do is to put D4 star here as 0 minus 1. The effect this has, this has now built a further toric, slightly bigger toric variety, in which the divisor corresponding to this cone has self-intersection -1. The self-intersection can always be computed by adding together the generators of adjacent rays, and you'll get a multiple of this ray, and that multiple is minus this intersection number. So let me make a note of that. Mark for toric surfaces, for non-singular toric surfaces, I should add. It is easy to determine the intersection numbers. So if you have a piece of a fan that looks something like this, let's say with vectors v1, v2, and v3, with these corresponding to the boundary divisors v1, v2, and v3, we have v1 plus v3 plus d2 squared v2 has to be equal to 0. So in other words, you can just read off the intersection number if you know v1, v2, and v3 by seeing which number here gives you 0. So for example, this plus this minus this is 0. Okay, so far so good. We're just pretending as if this was toric variety. I can continue this process. I then write down another cone. I'll take to be generated by D5 star. Again, that goes there. This is given by -1, 0. And you'll notice that this plus this plus minus this is 0. So again, that is what we'd get if we were trying to write down a toric variety where this curve, the corresponding divisor to this curve, has some intersection -1. Okay, so now things go a little bit wrong because we could actually try to continue this. We say, okay, D5 star, also, D5 should also self-intersection -1. And that means I should put D1 star, this all being cyclical here, D1 star is going to be equal to minus 1, 1. Again, this plus this minus this is 0. So that gives us, forces this to be a minus 1 curve, or the corresponding divisor to be a minus 1 curve. Now you'll notice something's gone wrong. I now have two D1s here. I started with a D1 up here. I kept on gluing together these various charts. And when I get back to D1, things don't match up. And let's just do this one more step. Let's go back to D2. So use the chart for in the star of D1. And okay, this is now D2 star goes here, and that will be equal to 0, 1. I got a chart here. So now I have two copies of the cone generated by D1 star and D2 star, and they're different cones. This is not a globally defined chart on my manifold B. So now the point is that these things get identified. These should be identified by the linear transformation. Well, let's see, D2 star 0, 1. This copy of 0, 1 should be identified with this copy. Oh, sorry, this copy of D2 star should be identified with this copy of D2 star. So 0, 1 should map to 1, 0. That tells me I should have 1, 0 in the second row of second column matrix. And minus 1, 1 should be mapped to 0, 1. So minus 1, 1 should be mapped to 0, 1 means I should have a 1, minus 1 here. So this linear transformation I've just written down, if I've done it correctly, sends minus 1, 1 to 1, 0, to 0, 1, and sends 0, 1 to 1, 0. So it identifies this cone with this cone. So this is an example of an affine manifold with a singularity. There's no way to extend the singularity across the origin. If you want, you could almost think about trying to make this out of paper, except paper, you're only allowed to, linear transformations that preserve a sheet of paper always have to be isometries. So this is not an isometry. But somehow, think about taking a piece of paper, cutting it along here, and then gluing this sector to this sector. You can't quite do that, but that's roughly what you get. So you get an affine manifold with a singularity at the origin. And this is typical of what you get. Okay, so I hope that makes some kind of sense. This is something you can do now to any, for any log Clavier. It's easiest to think about these for surfaces. For surfaces, you always get, let me just sort of draw this schematically now. You can think of this as looking something like this, where you have some singularity here. And then you can, there are various fun games you could play. For example, think about what a straight line is, what do straight lines actually do on these things, and so on and so forth. Maybe it's good to give one more example just to show some of the behavior that can happen. Let's do one more example. If you take a surface XD, where X is a surface, and D is a cycle of -2 curves instead of -1 curves. Doesn't quite matter how many I take, but you can find examples where you have between 1 and 9, well, 2 and 9, such -2 curves. And what this looks like, if you start with one of these curves, I'll draw it vertically. We might have D1 star, D2 star, D3 star, D4 star, and these are given by 0, 1, 1, 1, 2, 1, 3, 1, and then we repeat, we go back to D1 star, which is 4, 1, and D2 star, which is 5, 1. And then as before, you want to identify this copy of the cone generated by D1 star and D2 star with this copy. And this would be given by the matrix, let's see, so 1, 0, 1 gets mapped to 4, 1, and 1, 1 gets mapped to 5, 1, so I could do this matrix. And then it's kind of fun to think about what happens to straight lines on this thing. What you'll find is that if you, for example, come in at some angle here, a straight line like this will start to spiral around the origin and never quite reach the origin. Of course, every time you come to the edge here, you have to pass over here via this gluing. You get some kind of crazy line that wraps around, never quite reaches the origin. Okay, so there was our affine manifold, and that was something we thought we needed because affine manifolds play a key role in SYZ conjecture. Now, the next thing I hinted at again in the last lecture is that we want to build the mirror to XD, and the mirror is going to be some complex manifold or something like a complex manifold, which will involve some kind of corrections. So, moral, what we are looking for. We want to build. Actually, it turns out that what we were going to build is not a complex structure on X of B, but a complex structure on X check of B. Because that's the correct thing for the mirror for us. And this will be determined by certain kinds of corrections. So the first thing I want to do is give you the data structure which encodes corrections to the complex structure. So we'll first define a data structure. Which encodes corrections, and then in later lectures, we'll understand where the corrections come from. Okay, so I'm going to have to go through now, hopefully so far these definitions weren't so hard, but now I have to go through some slightly more complicated definitions. So from now on, I want to fix some auxiliary data. Fixed data of a submonoid E contained in the second homology of X, satisfying the following properties. So we would have, first of all, P is finitely generated, finitely generated monoid. Secondly, I want the set of verb elements in P, so P intersect minus P should just be the torsion elements of second homology. Very few examples actually have torsion. Occasionally, torsion does play an important role in some of the string theory, so worth mentioning that this will come in, but generally just assume there's no torsion or divide out by torsion. Third condition is I want P to be saturated. What does that mean? If you have some element A in H2 of XZ with M times A in P, or some positive integer N, then A is also in P. And finally, the last condition is that P contains every curve class represented by a stable map F from C to X with C genus 0. All the curve classes are actually represented essentially by rational curves. So I'm interested, so this should look very similar to the setup when we talk about toric geometry. We talk about a monoid ring, C bracket P, and the spectrum of C bracket P is corresponding toric variety. So here we should think spec C bracket P is, or maybe an open subset, an analytic open subset, is the Kähler moduli space of X. So I think this got alluded to in the last lecture that you have something called the Kähler moduli space. I don't want to go through the whole sort of physics origin of the notion, compare it with this. But if you are familiar with the Kähler moduli space, this really is going to be essentially the same thing. And so the idea is that when you build a mirror, on one side, you have a Kähler moduli space, and the mirror family, the complex moduli space should look something like the Kähler moduli space. So our goal will be construct a mirror family to X. Over spec C bracket P. So for X, spec C bracket P plays the role of the Kähler moduli space, and then for the mirror, it plays the role of some base of a family of mirrors. Now, this can't generally be done. And instead, we will have to work formally. Constructing mirrors over spec C bracket P mod I, each monomial ideal I with C bracket P mod I Artinian, so finite dimensional C algebra. Okay, so we do this for every possible ideal, or every possible ideal generated by monomials where this ring is finite. And this will allow us to eventually build a formal scheme as a mirror. This will allow us build a formal family. So I don't want to go through, I know you aren't algebraic geometers, so I don't want to belabor this point. But the important point is that this family will be formal. Generally, that's how we deal with convergence problems in algebraic geometry. We work with formal power series and don't worry about convergence. Ideally, you would really like this construction to converge in some analytic open sets and Euclidean open set. But we can't always, I mean, that will be quite hard to prove. Okay, so this is the auxiliary data we're going to need to construct, and you should think going forward that we're going to be specifying data that allows us to construct a family over such a scheme. Okay, so I think the next definition is going to take a little bit of time. So let me maybe pause for questions and then see whether this might be a good time for a break. Okay, so I'm going to define some structures, what we call wall structure, which you should think of, as I said, it's going to be a data structure for constructing these families. So this is a little bit technical, but bear with me and hopefully it will make sense. So from now on, let's fix the monoid P as above and a monomial ideal I inside C bracket P such that, now I'll give a name to the quotient A sub I at C bracket P mod I is a finite dimensional C vector space. And you should think that we're ultimately going to do this construction for every such I. The definition, a wall in BP is a pair DFD, where, first of all, D is contained in some sigma in P, is a dim X or dim B minus 1, so codimension 1, dimensional rational polyhedral cone. So being codimensional 1 is what makes it a wall. It separates different chambers. And what's FD? FD is a polynomial. FD is some polynomial of the following form. We'll have some summation over M in lambda D. I'll define them in a second. Some A P I. Or maybe I don't need to include that. P C M A T to the A, Z to the M, in AI bracket lambda D. So what does this mean? So here lambda D is the tangent space of integral tangent vectors. So here lambda D is the lattice of integral tangent vectors by the way, Daniel, just check, you are recording? Did you restart the recording? Okay, good. Okay, so lambda d is the lattice of integral tangent vectors to d. So this is a Dmx minus one-dimensional lattice. Here, t to the a represents an element of AI. AI, remember, is C bracket P mod the ideal I. So it's just a generator of C bracket P with exponent A. But we think this is an element of the quotient ring. And Z to the M is an element. This is now the monoid or group ring of lambda D over the ring A sub I. That the M represents an element. Represents the element of the monoid ring, or in this case, group ring. AI, right, lambda D corresponding to M. Okay, so this is a polynomial of some sort. It has coefficients CMA. These will just live in ground field C. And again, just to repeat, the TPA defines a class in this ring AI, and the ZVM corresponds to elements in lambda D. Okay, and then finally, this should satisfy the property here we require the FD come to 1 mod the ideal generated by all generated by things of the form T to the A and P minus A not in P. So generated by all the non-invertible elements in P. So this is well, okay. I'll just leave it like that. Okay, so you should think of this as a function as just 1 plus some corrections that have to do with curve classes. So that's what a wall is. We're going to see what we do with these walls in a moment. They're just codimensional objects separating two chambers, or possibly separating chambers. And then a wall structure. And you also see in some of the things that were written, scattering, the term scattering diagram. Is a finite set of walls. Okay, so this is the data structure which is going to allow us to determine certain families. So I'm not telling you how to construct them yet. That's going to come in a later talk. For the moment, let's just take as given a wall structure. So what do we do with wall structures is the next question. Okay, so a little bit more notation. We'll let D be a wall structure. So if I were to draw, maybe I'll attempt to draw what you should be visualizing here. So in 3 dimensions, for example, here we have our original BP and some complicated cone complex. And then inside here, we have maybe some mess of these codimension 1 cones doing all sorts of crazy things, maybe subdividing this in some crazy way, but nevertheless, there'll be a finite number of such cones. There's some complicated picture like this. So eventually I'll do some 2-dimensional examples where it's actually easy to visualize these things. Okay, so let's define the support of D. To be, so this is just the set of the union over all D, well, take the union over all elements, all walls in D, and just take the union D. So that would be this blue locus, this union of all of the walls. And then I'm going to define the singular locus of D, of a singular set, to be sing of D. And this is going to be delta. So remember, I define delta as the union of codimension 2 cones in P. So just remind you that's union sigma and P dimension sigma. It's dmx minus 2 sigma. And then I throw in all the boundaries of walls, so D, FD, in P, boundary of D. As a codimension 1 cone, D is a codimension 1 cone, so the boundary is a union of codimension 2 cones. And then finally, one more piece, I take two cones, 2 walls inside D, take the intersection, provided the intersection is codimension 2. Space here. Okay, so wherever 2 of these cones meet transversely in something that's codimension 2, I throw that into the singular locus. The boundary of a cone of a wall is in the singular locus, and the original singular locus of B also lies in the singular locus. So just as a 2-dimensional, let me remark as if dmx equals 2, then the singular locus of D is pretty simple. It's just the origin. The only thing that's going to happen is we have, here's BP, looking like a fan of some toric variety, perhaps. And then the wall structure of the scattering diagram will be a union of walls like this. Of course, these walls only intersect because they're cones. They only intersect at the origin in this case. And so the origin, which was already codimension 2, already lies in here. And hence the only singular locus, part of the singular locus is the origin. In higher dimensions, it's be more complicated. That's the support in the singular locus. Okay, now a little bit more information, a little bit more notation. So given a point X in the support of D, but not in the singular locus of D, define F sub X is the product over all D, FD in D, with the point X being in D of the corresponding function fd. So just already in two-dimensional ones, suppose you put your point x over here. The point is, I drew only one wall here, but of course you might have many, many different walls sitting on top of each other, each carrying its own function f sub d. So what I'm going to do is I'm going to take product of all those functions. So that will depend on x as you vary x, of course. For example, if x moves over to the point here, point x prime here, fx prime is 1 because x prime doesn't lie on a wall at all. But fx might be a product of wall functions, non-trivial product of wall functions. Okay, so that's the notation fx. So now what I'm going to do is I'm going to define a bunch of standard pieces. These will be schemes. These look a little bit, as you'll see in a second, these are going to look a little bit like they're standard pieces of a torus vibration. And then we're going to glue them together in ways dictated by these walls. Okay. So for any point, the next the point x in B, but not in the support of D, or maybe in B0, but not in the support of D, x in the interior of a maximal cell. So interior, actually, let me reword this. X in the interior of sigma minus the support of D, or sigma in P, a maximal cell, a maximal tenant. We associate a torus, an algebraic torus, which I'll write as U sub x. This is defined to be a spectrum, A bracket I, or A sub I, bracket lambda sigma. So this is an algebraic torus over spec of AI. So in other words, UX, i.e., UX can be thought of as being the torus lambda sigma tensor C star. So the torus algebraic torus lambda sigma tensor C star, but then cross this little base scheme spec AI. We're going to be building something over spec AI. So this is a trivial family of algebraic tori. Okay, so I'm going to associate with every such point, I'm going to associate such a torus. And furthermore, if X lies in the interior of a codimensional 1 cell minus the singular locus of D, the rho and P codimension 1 cone, we assert or we define another local model, another gadget, which I'll also write as U sub x, and this is slightly more complicated. Spec A sub I, bracket lambda rho. So lambda rho, just as before lambda D, was the space of integral tangent vectors to D, lambda rho is integral tangent vectors to rho. And then I'm going to throw in numeral variables z plus z minus, but I'm going to define a relation between these variables, z plus times z minus f sub x. That was this f sub x defined a little bit earlier. That depends on depends on the point x. So I have the equation z plus, I'm dividing it by z plus times z minus equals fx times t to the xp. So here, recall not xp, x rho. Here x rho is a one-dimensional stratum. Recall x rho is morphic to P1 is a one-dimensional stratum. So by the assumptions on P, necessarily the curve class of x rho lies in P. So this is the homology class of x rho. This lies in H2 of x, z. Okay, so I have some equation that looks like, roughly, if we ignore this, this is going to be correction term, which we're going to take into account, understand better later. If we ignore this correction term, this looks like z plus times z minus is equal to t. So it's kind of some kind of smoothing of z plus times z minus equals 0. So if I were to do this in 2 dimensions, let me just do a quick sketch here. We would have something like this. And again, I would have a scattering diode sort of wall structure that looks something like this. And associated to a point, if x is over here, we have ux is just a copy of c star squared cross spec ai. But at a point on a codimensional 1 wall, ux is a partial smoothing of something that looks like C star cross, let's say, spec C bracket X, Y, or maybe I should use the same notation, Z plus Z minus, mod Z plus Z minus. Okay, so in other words, if you set this this to be 0, of course, fx doesn't matter. You just get z plus z minus equals 0. And then once this is non-zero, you're getting some kind of partial smoothing. So this looks like some kind of partial smoothing of this cross C star. So if you want, you can think of it as a little bit of a smoothing. Try to draw it. Again, this is just getting intuition, sort of a little infinitesimal neighborhood of this that starts to smooth out this node here plus C star. Okay, so these are the things I'm going to call local models, and I want to start gluing together these various schemes in a way dictated by this wall structure and the combinatorics of the affine manifold with singularities. So let me first explain what's going to happen in the interior of a top-dimensional cell. So if x and x prime lie in the interior of sigma, minus the support of D. Let's choose a path, and here with sigma a maximal cone. There's some kind of problem with my pen here. Sorry. Right. So for sigma maximal cell, sigma P a maximal cone. Let me try to draw what this might look like. So of course we have maybe that's not good. My cone's always standard simplices, standard cones, and then maybe we have some complicated set of walls. All these sort of cones like that. And then we have 2 points, X and X prime. I want to choose a path connecting X and X prime. Gamma connecting X and X prime. So in other words, this will be, doesn't need to be an injection, atom sigma with image disjoint from the singular locus of D. I'm going to choose a path, something like this. Now let me draw a blow-up picture of this. Instead of trying to draw a 3-dimensional picture, let me draw a slice of this so I can draw a nice 2-dimensional picture. We have something like this. And then we have these various walls, something like this. And we have point X here and point X prime here. And I've chosen a path which avoids any intersections of these walls, transversal intersections of the walls. Something like this, gamma. Here, gamma of 0 is equal to X, gamma of 1 is equal to X prime. Okay, so what I want to do, well, this will allow us to define an isomorphism, which I'll write as T sub gamma from UX prime to UX. And this is given by something called a path order product. So to define this isomorphism, I'm going to go in the opposite direction. I'm going to define the isomorphism of the corresponding rings. So this is done by building an isomorphism of rings. Or as T gamma star, this will go from AI bracket lambda sigma to itself, AI bracket lambda sigma. Given by composition wall crossing automorphisms associated with the walls crossed by the path gamma, composed in the order crossed by gamma. Okay, so what I'm going to do, I'm going to have a composition of automorphisms. Every time this path crosses a wall, I'm going to have one automorphism of this ring AI bracket lambda sigma, and I take the composition of those automorphisms. That's why we call it the path order product. It depends on the order of walls traversed by the path. So I need to tell you what the automorphism is for a single wall crossing. So let me draw a picture here. So here's the wall D, FD, and here is the path gamma. And I need to define a wall crossing automorphism. So the wall crossing automorphism associated with crossing one wall is given by Z to the M gets mapped to some power of the wall crossing function of the wall function FD to the power n divided on m. I will define n in a second, times Z to the M. So remember that Z to the M represents an element, n is an element of lambda sigma. Where n is an element of lambda sigma, and n is an element of lambda sigma dual, is a primitive vector, primitive or a covector, if you will, a primitive normal vector to D, i.e., not divisible on not divisible in the lattice lambda D dual, lambda sigma dual, and it annihilates every tangent vector to D. And finally, so that determines the normal vector. This determines the vector n up to sign. Finally, there's a sign convention. So this only determines n up to sign. But the requirement that n should be negative, let's say if at time t0 is when we're crossing the wall, n should be negative on the tangent vector to gamma at time t0. So here we have gamma of t0, and the requirement essentially is that n be positive on the half space that gamma is coming from, and negative on the half space that we're going into. So that's this requirement that n that is negatively on the tangent vector to gamma t0. This determines n uniquely. Okay, so this is the wall crossing transformation. This is very fundamental throughout this business. It shows up in many, many different places. We don't yet know what we should take to the FD, but this is how these corrections, the FD is going to code corrections, the complex structure, and this is essentially, this kind of transformation is essentially what those corrections do for us. Okay, so this completes the definition of this T gamma star, because we just take the composition now. I've now told you what happens every time we cross a wall. We have this very simple form for the wall crossing transformation, and then we just take the composition this with this, with this, with this, with this. That gives us the map between rings, which then gives a map between the spectra, between the corresponding affine schemes. And that gives us, of course, that reverses the direction. So I'm going to go from ux prime to ux. Okay, so that defines these transformations. So now comes a crucial definition. Say D is consistent in codimension 0. If this T gamma is independent of the choice of the path gamma. Okay, so it turns out, so of course, if there are no walls, if we were simply in something like this where there were absolutely no walls, it would be consistent because this map, the map T gamma, would just be the identity. There's no wall crossing whatsoever. But as soon as we start having walls, this consistency becomes an incredibly subtle condition. And if I have time, I'll say some words about the complexity that this consistency condition can generate. But what it allows us to do for the moment is it allows us to simply identify all of these tori, all of these ux's. So if D is consistent in codimension 0, we can identify all the ux's for x inside the interior of a single cell for sigma maximal. We can identify all these ux's canonically. But notice it's non-trivial, as long as there are actually some walls. Okay, so that's consistently in codimension 0. Now, so far, if you recall, I had two sorts of of these things I was calling models. So we have these ux's, the first set of ux's, which I've been talking about. Sorry, I should have been, sorry, I was slightly sloppy down here. Well, no, maybe that's, okay, sorry. All right, so we had these kinds of ux's, which are just algebraic tori. I've now just shown how to identify all of those if we are within a single chamber, a single maximal cell. But I also have these other kinds of ux's. And that requires a little bit more explanation. So now, if X is instead lies in the interior of a codimension 1 cell, does not lie in the singular locus of D. Let me draw a little local picture of what's going to happen there. So we have some picture like this. Here's rho, here codimension of rho 1. So we might have some walls in scattering diagram or in the wall structure, something like this. And we have our point X here. And let's choose cones. Okay, give the adjacent maximal cones, rho contained in sigma, sigma prime maximal cone. And let's choose points, let's say X plus and X minus near X. X plus in the interior of sigma and X minus in the interior of sigma prime near the point X. And by near, it means that I can connect X plus to X and X minus to X without crossing any other walls other than the wall X itself is containing. So we choose these near X so that there are paths connecting X plus to X and X minus to X, not crossing any walls. Except those containing X. Okay, and I need to choose once and for all for each such point. I need to also, well, maybe I should be a little bit more careful. I want to choose a tangent vector for each row. I want to choose a tangent vector C plus. Which I'll point over C plus is there. So choose also once and for all a tangent vector C plus in the tangent space to sigma, so that the tangent space to rho and C plus generate lambda sigma. So this is something I should have chosen at the beginning. Okay, so I want to describe ux plus and ux minus as open subsets of ux. So I have, just to recap, I associate to each of these 2 points, we have this thickened algebraic torus, this algebraic torus over spec AI. And then at X, we have this u sub X, which is this more complicated thing. And so I want to define maps. So in other words, I want inclusions ux plus included in ux and ux minus included in ux. And to do this, I just go to the level of the rings. I have, sort of corresponding to this, I have the ring AI bracket lambda rho bracket z plus z minus modulo z plus z minus fx t to the x rho. That was the ring defining ux. That corresponds to ux. And I need to define maps to the rings associated with ux plus and ux minus. So for ux plus, I will take, that's AI, bracket lambda sigma. And this map is given by, well, z to the m maps to z to the m for n in lambda rho, and z plus maps to z to the c plus, that was my chosen tangent vector. And then I have to be much more careful about what happens to z minus. Z minus gets mapped to z to the minus c plus times fx times t to the x row. I hope this can be read. I'm trying to make this a little bit bigger here. Hopefully that's still visible on your screens. So what's going on, again, this lambda rho is just sitting inside lambda sigma. This is the tangent space to integral tangent vectors to rho. This integral tangent vectors to sigma. So of course, this is a sublattice of this. So I can just set z to the m to z to the m for any n tangent to lambda rho. I send z plus to z to the c plus. But then I have this equation, and that leaves no choice but to send z minus. Well, I solve for z minus in this equation. Z minus is z plus inverse times fx times t to the x row. And that's what we have here. Z plus is being sent to z to the c plus. We have z to the minus c plus times fx times t to the x row. So it's easy to see that this is sent to 0 under this map. Okay, so it's also easy to see that this is just a localization. This is the localization map. In which we're simply inverting z minus. Or maybe I should say invert z plus. And that means that this map actually is an open, the corresponding map of spectra is just an open embedding. Okay, so that allows me to describe ux plus as this is a torus sitting inside here, and I have a similar map for ux minus. So for ux minus, let me write this down, get a different color. This maps to a I bracket lambda sigma prime. And again, I have z to the m maps to z to the m for n lambda rho. This time z plus gets mapped to z to the c plus times fx times t to the x row. And z minus gets mapped to z to the minus c plus. And again, you can check that this satisfies the given equation. Okay, so this gives the desired inclusions. So now, what we get, so thus, what do we have? For each maximal cell, for each maximal cone sigma in P, we have a torus, which I'll write u sub x for x in the interior sigma, minus support of D, and for each row in P codimension 1, we have for x in row minus singular locus of D, we have u sub x, and then along with gluings, or along with identifications, ux plus, ux minus as open subsets of ux. Okay, so we can try to glue. So the picture now is that we have lots and lots of schemes, and we have various identifications between sort of two, ux and ux prime can be identified for x inside a maximal cell, and we have these ux's for x in codimension 1 cells, and we have open subsets there. So we can start to do lots of gluing. So glue all these open sets, all these ux's together. So again, let me try to, I don't have much more time, so let me sort of try to show you what happens in in dimension 2. It might seem like a lot of data, but the point should be that's sort of fairly simple. So here's BP, and then we have the wall structure, which is a bunch of rays. And now we have a open set. We have a UX here, UX1, UX2. These are just tori, so these would be sort of copies of C star squared spec AI. Over here, and these get identified, these two, because they're in the same maximal cell, get identified. But this UX1 can then be identified with a subset of UX3, as would be UX4. So these are identified with subsets. These are identified by an isomorphism. UX5 goes here, UX6. These have isomorphisms, and then maybe UX7. We have inclusion of UX7 there, and UX8 has inclusion there, and so on. So, associated to every one of these points, we have or every chamber, if you will, this wall structure, you have one of these models, one of the UXs, and we start to glue them together by gluing adjacent copies of these things. So we get something, we get a scheme. There's one slight condition that has to be checked. So I define consistency in codimension 0. I don't want to go through the technicalities in codimension 1. Consistency in codimension 1 guarantees that if we glue together all of these UXs using the isomorphisms, E gamma, and the open inclusions above, we get a well-defined scheme. Which I'll write as X sub I, D, circ. So here the dependence is the ideal. This was the chosen monomial ideal. This was the chosen wall structure, which needs to be consistent in codimension 0 and 1. And this, I will have to explain next time what's going on. This really should be an open subscheme of the thing we're really trying to compute. Okay, so I think, sorry, this was a rather technical second half of the lecture. It's not really that hard, but I think it takes a bit of getting used to all the how you use the status structure. So I think at the beginning of next lecture, I'll go through some concrete examples. Hopefully life will look a little bit simpler once I go through the examples. So let me stop and see if there are any questions.